Okay, welcome back. The demo I'm going to do now is called a rotating Planck and a falling ball. So it's an interesting demo, and you can actually do a good physics problem with this. Right? So we have a Planck here, uniform. We're assuming the mass is uniform, and it's pivoted about the end, right? And then the idea is we have a ball here at the end, and then we have a cup that we're going to place at a certain location on the Planck. And so I'm going to be dropping this, letting this rotate at the same time that I drop the ball. The initial height of the ball above the plane of the Planck, so if you go like this, the initial height of the ball should be roughly about the same height as the cup, like this. And so the question is, first of all, where should I place the cup? What's a good optimum location where I place the cup so that when this rotates, the cup is underneath the ball? And the second question is, what's the angle that I should have it? What's the greatest angle? What's the least angle? What's the optimum angle? So let's calculate that. It's easier to answer the first part of that question, where should the cup be placed? We want the cup to be able to accelerate faster than the ball, so that by the time that the cup is down here, the ball is able to land in the cup, right? So what is theta required so that the ball lands in the cup? Okay. So the first part of the question, if the length of the Planck is L, right, that part is easy to answer. Imagine the angle of inclination of the Planck is theta. So if the ball is exactly starts at the tip of the Planck, right? So the ball is also a distance of L from the pivot point, right? So the ball is going to basically go down and fall down, and the location of the ball is going to equal what? The ball is going to go straight like this. So it's going to be L cosine theta, right? So the location of the cup should also be at the same location where the ball is going to go, right? Because the ball is traversing a straight line path. So the cup should be placed on the platform a distance of L cosine theta from the pivot point, from the left pivot point. So if that distance is L cosine theta, this one is going to go like this. The platform will end up like this, right? The tip of the platform will be ahead of the ball, but the cup will be over here. And if the distance from here to the cup is L cosine theta, the ball will be able to land there. Okay, so the location here is L cosine theta, but then we don't exactly know what number that is because we have to calculate the theta. Okay, so now let's do a rotation problem. Okay, so when you have a rotating object like that, the first thing we want to calculate is the angular acceleration of the object, the angular acceleration. So we're going to say here torque is equal to I alpha, right? And then what are the torques on the object? Well, the torque is at the center of the Planck or platform, right? So it's equal to mg, and then the distance here is equal to L over 2. So the torque is equal to L over 2 mg times sine of this angle, right? But since we're using this as the angle that we are concentrating on, when we say L over 2 mg sine of that angle, that's the same thing as saying cosine of that angle. So I'm going to say L over 2 mg cosine of theta, and that's equal to the moment of inertia of the object about the pivot point. So since I'm using the end as my pivot point right here, it's going to be 1/3 mL squared times alpha, right? So then the m is going to cancel the m, the L is going to cancel the L, right? And then alpha is going to come out what? 3 over 2 g cosine theta over L. So all points of the object will have the same angular acceleration, right? 3 over 2 g cosine theta L alpha. Okay, so the next thing that we're going to argue is different points along the Planck are going to have a different tangential acceleration, right? So the tangential acceleration of the end is going to be the largest. The tangential acceleration of the center of mass is going to be half of the tangential acceleration at the end. So the further away you go from the pivot point, the larger the tangential acceleration, right? So what's the equation? A tangential is equal to r alpha. And then, so what does r mean? R is the distance of that point from the pivot point, right? That's going to be the r. So what's the tangential acceleration of the end of this rod? A tangential of the end. So since the distance here is equal to L of the end, right? So it's just going to be L alpha. So if I multiply this by L, the L cancels, and it's going to equal 3/2 G cosine theta. Okay? So then, here's going to be the restriction on what needs to happen here. When the ball is here, right, the ball's acceleration, as I drop it, the ball's acceleration is equal to G, right? It's this constant acceleration free fall. So then what I'm going to say is, what's the y component of the tangential acceleration of the tip of the rod? The y component. A tangential y. If that y component of the tip is greater than G, that means the Planck will start out falling downwards, this vertical motion. See, the Planck is going this way, it's accelerating this way, but if the y component is larger than G, that means the ball will always trail behind the tip of the Planck, right? So what's the y component? A tangential y. So what's this angle here? Okay, if this is theta, let's relate. Let's go like this, let's go like that. This is theta, right? This is theta, this is theta. This will be 90 minus theta right here, and then this will also be theta. So then A tangential y is equal to A tangential cosine theta. A tangential y. So then A tangential was, of the end was 3/2 G cosine theta, so that's going to be 3/2 G cosine theta times another cosine theta. So it's going to be A tangential y is equal to 3/2 G cosine squared theta. So what that is saying, that is telling us is that the y component of the tangential acceleration depends on the cosine squared. So if I were to release this from a very steep angle, right? What's this angle here? As the angle is approaching 90, what's happening to the cosine of 90? Cosine of 90 is getting less and less and less, right? The y component of the tangential acceleration is going to be small, right? So what's going to happen? This is going to accelerate faster, hit the tip of the Planck, and maybe bounce off, right? So, even if it doesn't necessarily hit the tip of the Planck, let's say I had it like this, a little bit ahead of the Planck. It's going to accelerate so faster, and then the Planck is going to go like this, right? And the ball is going to end up becoming lower than the Planck, right? So that means this large angles are not very good for this experiment. As the angle gets lower and lower, what's going to happen? As the angle gets lower, theta gets lower, that means A tangential increases, right? A tangential of the end increases, and then the y component also increases, right? Not only the tangential component of the end increases, its y component increases, right? So then, if the initial angle that I release it is such that the A tangential y is larger than G for the initial angle, as I release it, what's going to happen to the angle? It's going to keep going down, 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 down. That means A tangential is getting larger, A tangential y is getting larger as the thing is swinging, right? As the thing is swinging, the A tangential is increasing, A tangential y is increasing. So if the initial value of the y component is larger than G, then I know all subsequent values of A tangential y will also be larger than G, right? And that means the ball will always trail behind the platform, and then the platform will fall quickly, and then the ball is going to come and nicely land on the cup. Okay? So this is the requirement for the cup to be able to catch the ball. Okay? So then I now solve for cosine of theta. Cosine squared theta is greater than, so G cancels, so it's greater than 2/3. Okay, so why did I say less? Well, because if cosine of the angle has to be larger than that, right? Larger or the same as, I can say. That means since cosine increases as the angle decreases, right? So that means the angle must be equal to, this is the largest angle it can be. This is the initial angle, right? This is the largest initial angle that it could be, and it has to be less than that. Anything less than that, the Planck will always be ahead of the ball, okay? I've got a platform here, and let me see where I place the different cups, right? So then, let me measure the length of this 1 centimeters, 81 centimeters, and I've placed one of the cups at 70 centimeters and another cup at 50 centimeters. Okay? Okay, then I place this at 70 centimeters. Okay, and then I'll place the other one at 50 centimeters. Now, since I've already placed the cups at that location, and remember the location of the cup has to be L cosine theta. So that actually tells me if the location L cosine theta, right, that's going to be what? So my L is 81 centimeters, and so if I place the cup at 70, that already tells me what I should make the angle, right? So in this case, since I already placed the cups, I already know that 81 cosine theta needs to be equal to 70. So cosine theta needs to be equal to 2 degrees. So if I incline this at 30.2 degrees, will that work? Well, as long as I'm less than 35, it should work, right? Any angle less than 35 should make this work, okay? So then that should work. How about the 50? Will the 50 work? Well, what that is saying is, if the Planck falls, the cup will be right under the ball. But then that's greater than 35.3, right? So if I put the Planck at 51.8, it should be able to catch, in other words, the cup is in the right location for 51.8, it's in the right location, but the equation tells us it should not be able to catch. So we can practice both of this, see if it's working. Okay. See, the ball caught it. Let's practice that again. You just have to make sure that the angle is 30 exactly. Okay? And then the ball is right at the height of the cup, at the tip of the platform, and release them at the same time. Nice. He was able to catch it. Okay? Okay, now let's make it at the angle of 51.8. 51.8. So this is a really steep angle. Okay? So you see what's happening is that as it's falling, the ball, the location is right, but the ball is actually landing before the cup is, so the ball is hitting the bottom of the cup. Okay? So it's kind of coming down, and since it accelerates faster than the cup, right, it hits the bottom. Okay, so you see, with the 51 degrees, even though the location of the cup was correct, and it ended up becoming below the ball, but the ball ended up accelerating faster. So it was sort of like this. It came down, the ball is accelerating. By the time the ball is here, the platform is probably something like this. And then the cup is here. Right? But the ball is here already, so it's past the height of the cup. The cup, right? And then by the time that the ball is here, the platform is like this. And the cup is something like this, right? And then by the time that the ball hits here, and then the cup is like this. So it's kind of like the front edge of the cup, right? Because it gets there quicker. The cup is always trailing behind the ball, and the cup is not able to catch the ball, you see? So you can see from this a good example of a rotational motion, torque, angular acceleration, tangential acceleration, and then setting the y component of the tangential acceleration to be larger than g, and then actually setting up a demo and seeing that it works. Okay? Thank you very much.